In part 2 of section 21, we're going to look at logarithmic equations, and for the first examples here, we're going to be seeing the one-to-one property of logarithms. So this is very similar to the one-to-one property of exponentials, and I'll start with the second line of the theorem 21.2. It says if log base b of m is equal to log base b of n. So you have to have one log on the left side of the equation and one log on the right side of the equation, hence why we call this a one-to-one property, just like with exponentials. Notice that the bases on these two logs are the same base, and then the arguments respectively are m and n. So if these two logarithms are supposed to be equal to each other, then the only way that can be true is if their arguments are equal to each other. Just like with exponentials, we said the exponents would have to be equal if they have the same base. So this property works anytime we have two logarithms equal to each other with the same base. Now the first line of this theorem gives us the restrictions on the logarithms that we can work with. So the first restriction says everything has to be a real number. Okay, no problems there. We've dealt with real numbers the entire semester. The base has to be greater than 0, and it can't be 1. And then there's also requirements here on m and n. Now these are requirements because m and n represent the argument. Arguments have to be greater than 0 for a logarithm, so that's why that restriction is there. Let's look at example 21.3. It says find the exact solution of each equation, and then there's an extra sentence here, be sure to reject any x value that is not in the domain of the original logarithmic expressions. So let's take a look at the first equation. We have log of 5x plus 1 is equal to log of 2x plus 3 plus log of 2. Now the left-hand side is a single logarithm with an implied base of 10. This is a common log. On the right-hand side, we do not have a single logarithm. We have two logarithms, but they do both have the same base, also 10. So what I'll do on the right-hand side is a condensing using the properties that we saw in section 20, so that way I can get that down to just one single log statement. So I'm going to copy down the left-hand side, log of 5x plus 1, and then the right-hand side has addition in between these two logs, which means I can combine them together with the arguments being multiplied. So this is going to become log of 4x plus 6. In which case, this equation now fits the one-to-one property perfectly. Single log on the left, single log on the right. They both have the exact same base, so we can just set the two arguments equal to each other. 5x plus 1 is equal to 4x plus 6. And now this gives us a nice linear equation. That's a polynomial equation. We can solve this for x. Subtract 4x from both sides to get x plus 1 is equal to 6, and then subtract 1 from both sides to finally get that x is equal to 5. Now, it mentions here that we are supposed to reject any value of x that is not in the domain of the original logarithmic expression. So I want to show you what that looks like before we go boxing in this answer. So for the check, I need to take 5 and substitute it in to each one of the logs in the original equation. So the first one has log with 5 times 5 plus 1 for its argument equal to log of 2 times 5 plus 3 for its argument, and the last one doesn't have x at all, it's just log of 2, so I don't have to plug anything in there. So the first log is actually going to be log of 26. The second log is going to be log of 13, and then of course we have log of 2. So what we're looking for here in terms of rejecting potential answers is we're looking at the arguments. When I take the 5 and plug it back in, does my argument fit the condition for being greater than 0? Now obviously the last log never had the argument change, so it's okay, it's 2. But the first two are 26 and 13 respectively after we plug in 5, both of which are greater than 0, so they're perfectly fine. That's what we're looking for when it comes to trying to reject any value of x that is not in the domain of the original logarithmic expressions. Since it works, I will box x equals 5 in as the only solution here to this problem. Part B, we're going to look at another example. We have 3 times log x is equal to log 25. Now, as a contrast with the previous problem, this actually is just a single log on the left equal to a single log on the right. However, I can't use the one-to-one property quite yet. And the reason for that is because of the implied coefficients that are in the theorem. There's an implied 1 as the coefficient for each log in that one-to-one property. Since I don't have a coefficient of 1 on the left-hand side, I can bring that up as a power. Since this is a logarithm, we have a property that says we can do that. Then I can write this as log of x to the third is equal to log of 125. Now I can use the one-to-one property and get that x cubed is equal to 125. Again, this gets us into a polynomial equation. It's not linear this time, it's cubic, but it's still a polynomial. And I'm only interested in the real solutions for this. And the only real solution for this is going to be 5. And if you take 5 and plug it back into the original equation, you will have no problem whatsoever making that one work. So we'll box that in. Let's take a look at one more example. Part C. I have log of 2x minus 1 is equal to log of x plus 3 plus log of 3. So this is a lot like part A, where I have the 2 logs on the left-hand side, or excuse me, on the right-hand side, and I need to take those and condense them before doing anything else. So the left-hand side looks good, log of 2x minus 1. Right-hand side is going to become log of 3x plus 9. They're both common logs, single log on the left, single log on the right. Let's set the arguments equal to each other. 2x minus 1 is equal to 3x plus 9. Subtract 2x from both sides to get negative 1 equals x plus 9. Then subtract 9 from both sides, and I'll end up with negative 10 is equal to x. Now if I take negative 10 and plug it back in to the original equation, if I plug negative 10 back in to that first argument, I'm going to end up with an argument of negative 21. If I plug it into the second logarithm, I'm going to end up with an argument of negative 7. Neither one of those are going to be permitted. All it takes is one of them to be not greater than 0, and it means that this answer is no good. So this ends up having to be a rejected solution. Since it was the only solution that we had come up with, that means that there is no solution at all for this. So I'll just write out the phrase no solution. Or if you prefer, you can use the 0 with a slash through it, meaning the empty set. And either one of these would be acceptable ways to state the answer for the solution to part C.